Yeah, I looked at all 7 questions. So question 1, I meant to be tricky. Most people said 6 because of Fermat's level theorem, but that doesn't mean that the first value for which something to the n is congruent to 1 is going to be p minus 1. In this case, it turned out to be that. But what you need to do in general is check all the powers and find the first one that's congruent to 1. But it turned out to be 6 anyway. We talked about congruences mod 3, so no issue there. We talked about modular exponentiation, I believe, the other day. And we talked through number 4. Number 4, basically, if you made a good effort, you got your 2 points. But there's some good logical thought applied to those. Euclidean algorithm, the GCD of all of these is 1 except for E, which was 139.
That messed with my head.
Yeah, me too.
I was like, what?
And the GCD should not be 0. Okay, 0 is not a divisor of anything. But sometimes when you're going through, you get to a 1 equals 1 times 1 plus 0. And you think it's a 0, but it's really a 1. The fact that these are maybe prime numbers tells you immediately the GCD will be 1, because there's no common divisor unless one's a multiple. 6 we talked about yesterday, and then Fermat's level theorem to the 23 to 1002 we talked about as well. So good job with the homework.
Just to be real clear on the GCD and algorithm, do you have to have the bigger number divided by the little number? It seems
Yes.
like you do, because otherwise you're going to end up with a 1 anytime.
Yeah.
Otherwise, you're going to end up with
1 all the time.
this.
Yeah.
And you've decided the GCD of 100 and 101 is the same as the GCD of 101 and 100. It's still true, but you haven't simplified your problem.
Yeah.
They got something wrong there.
The next one's going to be 101 equals 1 times 100 plus 1, which is
Right.
what you would get if you had it the other way.
Exactly.
So it's just...
Yeah.
So you should always flip the way.
Yeah, you want to start with the bigger number.
Start with bigger.
And if you have negative numbers, which I won't do to you probably, but if you have negative numbers, just do this with positive numbers and adjust the signs later. So, public service announcement. If sometime in your time at Clark you happen to encounter an earthquake drill,
Like in the next 6 minutes.
yes, the correct procedure is to get down underneath something solid. Hey, this would probably do nicely. And go underneath and hold on. So hold on to the table leg or something in case the building's shaking.
But you don't put your hand over your neck anymore?
You don't have to.
Can't keep up, man.
But you can.
You have to hope that the inmates that built the table did a good job, though.
Yeah. And then normally, once the shaking stops, there's an evacuation. We're not going to do that part today. We're just going to do the drop, cover, and hold part. But then normally you would evacuate and you would go to this area outside where the map is, and that's a designated meeting spot, so everybody gathers there and stuff like that. And I found out last time we did this, if you do evacuate, leave the doors open. Because if you close it and the building shifts, it can be impossible to get in. And if there's people trapped inside, now you got 2 problems. No, for an earthquake.
Well, oh, I thought you were talking about general evacuation.
No, just for earthquake. Although, yeah, if there's a fire in the earthquake, you'd want to block it. But yeah, I found that out last time. But anyway, that's just general information. All right. Don't need that anymore. We were talking about matrices, and I promised to tell you why matrices are so fun and lucrative. So we talked about matrix multiplication, right? And you've seen this if you've done matrices in 120 with me. If you have a series of equations, I'll just let's just say here's 3 equations, and they're random, so they might not have a solution, but they probably do. And you want to solve these simultaneously. Okay, first of all, why would you want to do this? Well, if you're doing KVL, KCL, you want to do this because you reduce your circuit to a series of simultaneous equations, summing currents or voltages, and if you solve them simultaneously, you can find what the unknown quantities are in your circuit. But there's a lot of other cases where you want to do this. Like I said, when you look at the motion of an object through space, and it's going through a series of translations or rotations, you can describe those with matrix operations, which brings them down to a series of simultaneous equations. If you're trying to balance a stock portfolio, how much of each company should I have in my portfolio based on their expected returns, based on the risk of them? Right? So you don't just find the best company and put all your money in that stock because the CEO might end up in jail tomorrow for some reason and your stock is worthless now. So you diversify. You get a portfolio of several or 100 or 1,000 stocks, and you buy pieces of each. How much of each stock should you buy to maximize your likely return? That's a classic problem in portfolio management. And it turns out you can write an equation which says, based on how much of each of these stocks I have, something's going to happen on the right side. And you can write one of these equations for each of your assets, and you get something like 5,000 equations and 5,000 unknowns. And if you can find a solution for that, you know what your optimum portfolio is. And if you're trading at a high frequency, like you're doing a trade every second, you need to solve those 5,000 equations really quickly. The other thing is, anybody here taking differential equations?
I'm taking it.
Okay, so diffie-qs are basically using calculus the way we use algebra for describing relationships among things. So you can take a system that's in motion, something that's changing over time, and you can write a series of equations to describe how the system changes from one moment to the next. And it usually involves partial derivatives. And if you can solve those equations simultaneously, you can do things like figure out, here's an airplane wing. If a bird hits it at this point, at this speed, is the wing going to fracture? Is the wing going to fracture after another 200 hours of airtime? So lots and lots of questions can come down to solving simultaneous equations. And here's the way that we solve them in 120. We use matrices. So if you make a matrix of coefficients, uh-oh, what's that?
This is a Clark College earthquake technique. Prepare now to drop, cover, and hold on.
Play classic.
This is the Great Washington Shakeout Earthquake Exercise. Practice now to protect yourself during a real earthquake. Right now, practice. Drop, cover, and hold on. This is a Clark College earthquake exercise. Drop, cover, and hold on. This is the Great Washington Shakeout Earthquake Exercise. Practice now to protect yourself during a real earthquake. Right now, drop, cover, and hold on.
You're allowed to talk, though. It's not like a lockdown.
This concludes the earthquake exercise. Thank you for taking part in the Great Washington Shakeout at Clark College.
Should I normally say this concludes the
Again,
earthquake?
this concludes
Yeah.
the earthquake
What,
exercise.
how many fatalities in the last 60 seconds? It wasn't even 60 seconds. It was 50.
Well, one of the ways you can tell how bad an earthquake is how long it lasts. So, this obviously was not a bad one.
It's like you could barely feel it.
My village did get attacked. The earthquake wasn't long enough to, like, rebuild my defenses. All right, thank you for doing that. So we can build a matrix of coefficients on the left, and we can make a 3x1 matrix of our unknowns. And on the right, we make a matrix of whatever the constants or whatever is on the right-hand side are. And if we think of these as matrices and we just do straight multiplication, we find the following. When we multiply this matrix by this matrix, this is 3 by 3, this is 3 by 1, we're going to get a 3 by 1 matrix. So first row, first column is going to be the dot product of the first row with the first column. Dot product, you multiply and add. So dot product of this with this is 5x plus 4y minus z. Second row, first column is the dot product of this row with the same first column, and that's going to be 3x minus y plus 2z. And third row, first column is going to be the dot product of this row with that same first column, negative x plus y plus z. So just multiplying this matrix by this matrix gives me this matrix. But if I can somehow arrange x, y, and z so that this matrix is exactly equal to this matrix, then the following must be true. 5x minus 4y plus 4y minus z must equal 6. 3x minus y plus 2z must equal 0. Minus x plus y plus z must equal 5. And I've satisfied my original system of equations. So if I could find a matrix x, y, z that satisfies this, that x, y, z will also satisfy these three equations. So how do we do that? And in what we basically have is we have some matrix of constants A, we have some matrix of unknowns, and we have some other matrix of constants B. And the question is, find x. Now, if this was regular algebra, it's easy. Divide both sides by A. With matrices, we can't divide. There's no division operation. But there is the next best thing. There's sometimes an inverse operation. But let's just take the inverse of a matrix.
Is it over already?
You missed it, man.
There wasn't at the end.
Yeah. Things were falling in flames. It's terrible. We can't divide both sides by B, but we talked about inverses. There's an inverse of a matrix. Maybe we didn't talk about inverse. If A is a matrix, there may be...
Yeah?
All clear. This concludes the emergency drill.
I already concluded it.
Repeat. All clear. This concludes the emergency drill.
Slow on the draw there.
Yeah.
Were we supposed to sit on there for 5 minutes?
Well, last time that they did, I think a lockdown, we never got the all
Yeah.
clear.
Yeah, that did that.
So they may be...
Maybe they're
There
compensating.
may be redundancy built in. If we have a matrix A, there's sometimes an inverse matrix. We can write A inverse with the following property. A inverse times A is that identity matrix, the thing with ones going down the diagonal. This does not always exist. Not every matrix has an inverse. Just like not every number has an inverse. 0 doesn't have an inverse. But if that inverse exists, here's what we can do. We can multiply both sides by A inverse on the left. And matrix multiplication is not commutative. A times B is usually not the same as B times A. So we have to make sure if we multiply on the left here, we multiply on the left here. If A inverse exists, this is the identity. So this becomes identity times x equals A inverse times B. And the identity is the identity because when you multiply by anything, it doesn't change it. So the identity times x is just x. Is just equal to A inverse B. There's your solution to the equation. So multiplying matrices is easy. The only tricky part is finding this inverse. And a lot of computing power has been spent calculating inverses of matrices. But if you can invert a matrix, you can solve these equations. And so in MATLAB, we have you do something like a raised to the minus 1 times b. And we got our solutions for KVL, KCL.
What exactly is the inverse of the matrix then?
It's a thing that when you multiply by a, you get the identity. How's that for a non-answer?
That's a really useful answer for you in the
True.
That's really
It's
the
got
only
some weird formula you have to do to figure it out.
That's not a weird formula.
Oh.
Let me show you some inverses, though.
Nice. I remember when I was doing KVL and KCL, I learned about this function on the calculator called RREF, reduced row echelon form.
Oh, yes.
Is that something that's similar to the finding
Oh, yeah.
numbers? Okay.
Yeah.
Cool.
Are we going to learn row reduction?
No. But you will in linear algebra.
Oh yeah, I took that.
But we could just do it with that, correct? That's a different way to find the same thing that we're talking about right now.
Mm-hmm.
Yeah.
Okay.
So here's a matrix A. Hopefully I didn't pick a bad matrix. There's the inverse of A. So I can say B equals A inverse. Or let's say C equals A inverse.
Silent do fractions.
Just what?
Does silent do fractional form?
It does decimals. I don't know if it'll do fractions.
I was going to say, because that will look a lot better if you do fractions.
Yeah. So there's C, there's A. If I multiply them, I get something really close to the identity. Those 10 to the minus 16ths are supposed to be 0. And if I do A times C, I still get something really close to the identity. So yeah, we're not going to go into this because that would take us really far afield. But how do you find the inverse of a matrix? It turns out you basically do something like solving simultaneous equations, is one way to do it. You take your matrix and you try to put it in a form where it's got zeros up here and then interesting stuff down here. If you have it in that form, it's pretty easy to find the inverse. But this is the form that you put a system of equations in when you're trying to solve them simultaneously. You get one equation with just one unknown. So something times x equals something. That lets you solve x. Then you can plug that in here, and now you've just got one unknown, which is y. You solve that, you plug these in, you've got one unknown z, and so on. But there's other ways to do it. You can use the determinant, which is a whole other topic, and recursively find a solution for what the elements of the inverse are.
Now we can use that there.
Yes. And it's computationally complex. The bigger your matrix, the longer it takes in a much worse than linear way. I don't know what the exact growth factor is. It might be n cubed or something. It's pretty horrible. So if you try to do a million by million matrix with a conventional approach, it's computationally.
There's a lot of zeros in there.
Yeah.
Cancel a lot of it out.
If there's particular forms or lots of zeros, a sparse matrix, then you can.
Like what applications with solving a matrix that they have?
Well, the application for finding an inverse is to solve the matrix equation. The application for solving the matrix equation is to solve systems of linear equations.
So what system is that big that?
Oh, optimization problems. Like a portfolio was one I mentioned. You might have an asset of 5,000 different stocks, a portfolio of 5,000 different stocks. And so you got 5,000 equations and 5,000 unknowns.
Scientific research.
Scientific research, or if you're doing like study at home, stuff like that.
Meteorology is one.
Yeah.
Uses a whole bunch of variables.
Meteorology is crazy.
That's one way to put it.
Does it even work?
Sometimes. You know where you find the best weather predictions, though?
Outside.
Outside?
Even better. It's like long-term predictions, Wall Street. Because if you know how to predict the weather, you don't go on the evening news and tell people. You sell that information to people who want to speculate on things like wheat features. Because if you know if there's going to be a drought next year, you can make a lot of money. You can buy up on futures of crops, or you can short them, and that's valuable information. So
Oh, yeah, those
supposedly,
good meteorologists are actually stockbrokers, buying stocks.
Maybe by night. But yeah, today's weather is a really good predictor of tomorrow's weather. Statistically, that does a good job.
Unless you live in Washington.
Yeah. All right. Don't need the screen. I think that's all I needed to say on matrices. So let me talk about functions. And we know what functions are intuitively. We use them in math. We use them in computer programming and so on. But the first week when we were talking about sets, I mentioned that we can think of a function as just a collection of pairs. If we have some set A and some other set B and a function f, then for any element of A, f of A is equal to some element of B. So we might write f goes from A to B, f of A equals B. And we could represent this fact with simply an ordered pair, A comma B. Or maybe A1 comma B1, A2 comma B2, A3 comma B3, and so on, yeah, A n, B n. And there is a set of these ordered pairs that corresponds exactly to this function f. Right? So the set of all A comma B such that A is contained in A. Or the set of all pairs A comma f of A, where A comes from the set big A. That's synonymous with the function f. So we could define a square root function, or we could define a square function on positive integers with a set consisting of 1 comma 1, 2 comma 4, 3 comma 9. And it's an infinite set. But if we want to know the square of a number, we can just look in this set, find the ordered pair where that's the first element. And it captures the same information as the function. And this is a subset of, in this case, the cross product of z with itself. And in general, this will be a subset of A cross B. Remember, the Cartesian product or the cross of two sets is a set of all ordered pairs, where the first element comes from A, second element comes from B. This is a set of some particular pairs, where the first comes from A and the second comes from B. So we can think of functions as subsets of this Cartesian product. So, terminology. The domain of a function f is the set of points where f is defined. So it might be all of A, or it might be some subset of A. For example, if I have functions going from the real numbers to the real numbers, where f of x is the square root of x, the domain of that function is not all real numbers, because f does not apply to -1, -2. So the domain would only be the non-negative real numbers. And the range or codomain is a set of things that the function maps to. So the set of elements that are mapped to by something over here. So for example, if f goes from z to z. And f just takes an integer to the integer plus 1. The domain is all integers, and the range is also all integers. But if the function takes an integer to 2 times that integer, then the range is the set of even integers. So it may not be the entire set B. Yeah?
What would be the English definition of range?
I didn't give it to you because I'm blanking on the difference between range and codomain.
Okay.
But I can check my notes.
They are one and the same, aren't
I think there's a difference. I think one is the set you're mapping into, and the other is the set of things that you're mapping to.
they? One of them, well, you have domain and you have codomain. And you have domain and you have range.
So the range of f is the set of all f sub a. It's the set of all points that you actually map to. The codomain is just this set that we're defining f to go into. But that's not as interesting. This is also called the image of A.
Wait, A exists.
Image of F. What? Sorry.
A exists, and then there's a capital A.
This is the range is a set of down here.
Yeah.
The set of all f of A, where A is contained in the big set A. So the set of points mapped to so if f of x is 2x, the domain is all integers, the range is the set of even integers.
And so the codomain then is just the other set of integers that you're mapping to. But not,
So when I write my function like this, the codomain is all of z.
right. So it's not necessarily after the function is operated.
Right.
It's just the other set.
Yeah, it's just the
Okay.
set that you're defining on the other side. But range is more interesting, because that's the stuff that's actually mapped to from somewhere. So to be a function, we need one property in particular. So to be a valid function, it must be the case that f of x is unique for all x in the domain. Meaning if f of x equals the square root of x, technically that's not a function. Because the square root of 9 has 2 values, positive 3 and negative 3. So if we define a function f that takes a number to the number whose square is that original number, that's not a well-defined function. Because there's 2 possible values we might be mapping 9 to. We could be mapping it to 3 or negative 3. So f of x has to be uniquely defined for each x. Doesn't mean that every f of x will be different from every other f of x. It's not uniqueness in that sense. But f of x only takes you to one number. So this is a function. This is not a function. Okay, if that point is carried over to 2. And if you think of a function as just a set of ordered pairs, it's easy to define things that aren't functions. Right, if I contain the number 9, 3, and the number 9, negative 3, then 9 goes to more than one thing. It's not a function. So we'll pretty much only talk about valid functions. So there's three kinds of functions we're going to talk about. So we can say a function f is onto or surjective if, I'll give it to you in math B first, for all B in B, there exists an A in A such that f of A equals B. What does that mean in English?
What's the that for D again?
There exists. What this is saying is that for any point B over here, there exists a point A over here such that f of A is equal to B. In other words, every point in B is mapped to from somewhere in A.
The second arrow shouldn't be there, should it?
This one?
Yeah.
Those are just extra arrows. We can have other spurious arrows. But the one we're interested in is that bottom one.
I thought that was the one that showed it wasn't.
So for any point B that we find over here, we can find some point A over here such that f carries A to B. So that's called surjective, and sometimes we just say onto. In other words, you map to every single point in the codomain. So again, if we map from integers to integers where f of x is x squared, that is not surjective, because there's no integer that maps to 3. But if we restrict this to the set of square integers, 0, 1, 4, 9, and so on, then f would be surjective or onto. All right, so that's one property a function may or may not have.
Can you give more examples about that?
So that is surjective. Every integer is mapped to by some other integer. For example, the number 10 is mapped to by 15. F of 15 is equal to 10.
Okay, so every element in the range mapped to only one element in the domain.
It could come from multiple elements. This is perfectly fine.
The point being, though, that there's no element in the codomain that is not mapped to by
Right.
something in the domain.
Every point over here comes from something over here. If I have a point here and there's nothing mapping to it, then it's not onto.
Okay, so which means every function for any value of x on A must have a output in B.
To be well defined, every point here has to map somewhere.
Okay.
Okay, but we could have a function where everything maps to exactly the same point.
Right.
And then if there's a point over here that's not mapped to, it's not onto, it's not surjective.
Okay, so the first one is the defined function, the second one is defined function but not surjective.
When you
Right.
say that it's not onto, you're saying that B, the point B isn't one of the answers to the function A. So what you're basically saying is that B,
You were right there a minute ago.
so what that tells us is that B isn't a set of answers to A.
Right, basically, yeah.
Okay.
Okay, there's points that are not mapped to by anything. So let's make a clean map. Now let's put down some particular points. So here's A, and here's B. And I've got 3 points over here, and I've got 3 points over here. All right, if my function is well defined, I'm saying it's defined on all these points, okay? So if I have a map like this, is that surjective?
Yes, because every point of B has...
Every point of B is mapped from somewhere, that's a surjective function. If my function maps like this,
it's defined but not surjective because there's one point that's
it's not surjective because nothing is mapping to this. And if A happens to have some additional points, is that surjective?
Yes.
Yes, because every point in B is mapped to by something. And if we go back to this, it's not surjective because there's a point that's not mapped to. Okay, so surjective just says every point gets mapped to from something.
What about a point in A that's not mapped to anything?
Then the function is not defined at that point. So it's not part of the domain. So if it's a square root function, we don't have any negative numbers in the domain. All right, the next property is injective. Which is also called one-to-one. I'll give it to you in English first. Different A's map to different B's.
So each one has like a distinct set, right?
Each one goes somewhere distinct. So this is not injective because I have two different points mapping to the same value over here. But if I had 5 points over here, that is injective. Different A's map to different B's.
So like f of x equals x is injective, but f of x sine x isn't.
Correct. Perfect.
Does it mean there should be just a unique solution, or it doesn't?
There's not really a question of a solution. It's a function that's defined, and we're analyzing its properties. So if this is our function, we can look at it and we can say this is injective and it's also surjective. If there's another point in B over here, it's no longer surjective, but it's still injective. Because different A's map to different B's. There's a B that's not mapped that has nothing to do with injectivity. The third one's a combination, one-to-one and onto, or bijective. Bijective means it's both surjective and injective. So we can add another point here. That's surjective because every point is mapped to, and it's injective because different points map to, different A's map to different B's. So that function is bijective.
So every bijective function has to be injective and surjective at the same time.
Correct. Let me give you the math speak for injective. of A1 equals f of A2 if and only if A1 and A2 are equal for all A1, A2, and A. That's the more precise way to say one-to-one are injective.
Upside down A.
For all. Universal quantifier. Yeah, it's A for all, it's E for exists. For all or there exists. So one consequence, and you can think about this and see if you believe it, if a function is bijective, we can define its inverse. Because each point here maps to a point over here, and every point here is mapped, we can define an inverse function that just runs in the opposite direction. Let me call it F inverse.
So you can only define an inverse if you have a bijective function?
Yes, if it's not onto, if it's not surjective, we would have a point over here that doesn't go anywhere. And if it's not injective, and we have 2 points coming to the same point over here, the inverse would take that 1 point to 2 points.
And it's not a function anymore.
And it's not a function anymore. So for any function f, if it's bijective, we can define its inverse. And there's a simple function that I neglected to mention. It's a function from a set to itself that takes each element to itself. That's trivially a bijective function, and it's called the identity function. So if we look at the identity function from z to z, it just takes an integer and it maps it to the same integer. And it's a trivial function, but it is a function.
I was also going to mention a trivial function that the A maps to the 0.
Yes, so there's a 0 function. If you have something like integers, that takes every element to 0. That's not injective and it's not surjective, but it is a function. And when you have functions like f going from A to B, and g going from B to C, you can define composite functions, which say take an element of A, map it under F to an element of B, and then map that under G to an element of C. So if I have 3 sets, A, B, and C, and I have a function F here, and I have a function G here, I map some point to this point in B, and G maps this point to some point over here, I can define this composite function as a function from A to C. And I would write it like this. That's G composed with F. And I mention that only because F composed with its inverse is the identity function. And so it kind of starts to look a little like multiplication, and in fact you can define an algebra of functions. In fact you can do calculus on functions. It's called functional analysis. And you can talk about limits of sequences of functions and all kinds of great things like that. And that's a really cool branch of study. All right, and obviously we're using functions in computer science all the time, and some of these things will come up. But that's enough to get you through your next homework, I believe, and to let us leave this stuff behind. So tomorrow will be your quiz, and I'll give you full period for that. And then Monday we're going to start mathematical induction. So lots of proofs and good stuff. Yeah?
For the quiz, you get page notes? Or?
Page of notes.
Page notes.
Yeah.
Front and back?
Front and back. Go crazy. Yeah.
What's on the quiz? Like,
Everything we did up to the beginning of this week.
okay.
So set theory stuff was week 1, propositional logic was week 2, and basic number theory, prime numbers was week 3. Not the crypto stuff and such that we did this week. Yeah.
I need no purpose.
How many, what should the size of the report be? Can it be a full sheet of paper?
Yes.
Okay.
If you really want to bring in a big sheet of paper. I'll let you go 11 by 17. How about that?
Well, the usual page size is 11.5 by 8.
Correct.